All right, guys, so I'm just going to do my best here to kind of cover all the topics that you'll need to know from Chapter 6. Kind of a little review, I guess, rather than going back and watching all the individual videos. So starting with section 6.1, we did operations on functions. So adding, subtracting, multiplying, dividing, and then composing one inside the other. It's like the f of g and g of x. So I'm going to give you guys two functions. So we've got f of x equals, let's do x squared plus 3. And then g of x equals 3x minus 2. All right, so we are going to add, subtract, multiply, and divide these functions. Okay, so the notation would look like this, f plus g of x. This x does not mean you're multiplying by x. It really just tells us that's what the variable is. It's the same as this x right here. It's f of x. It means it's a function of x. So this is the function f plus g of x. It just tells us that's what our variable is. So we do x squared plus 3 in parentheses, and then plus 3x minus 2 in parentheses. You basically are just combining like terms. So the x squared doesn't combine with anything. The 3x actually does not combine with anything. And then we combine up the 3 plus negative 2, which gives us a positive 1. All right, so that'll be your answer for the addition. For subtraction, this is the notation that you would see to show you're going to subtract one from the other. Be very careful with subtraction. Make sure you've got a set of parentheses around especially the second function. So we've got x squared. Again, doesn't combine with anything. For the x, we have minus 3x, so that's a negative 3x. And then we have 3 minus negative 2. So 3 minus negative 2 ends up being a positive 5, because it's really 3 plus 2. Okay, next let's do the multiplication. Okay, so we're going to multiply one times the other, which is basically like foiling, and then combining like terms. So first we do x squared times 3x, and that's a 3x to the third. Outside we get x squared times negative 2. Inside 3 times 3x. And then last 3 times negative 2. Okay, so then combine up our like terms, and there aren't any. So that's our final answer. Fourth operation is division, f divided by g. And so we do x cubed plus 3 for our numerator, that's f, and then divided by 3x minus 2. So the only thing that we need to do here is figure out what would make the denominator equal 0. So I'll do a little side work over here. Okay, so this tells me that if I were to plug in 2/3, it would give me a denominator of 0. Well, I can't have a denominator of 0. So I throw on a little domain restriction here that tells me I cannot plug in 2/3. But other than that, anything else is fair game. All right, so let's do the composition too. So let's try f composed with g. That means we're taking our function f and then plugging in g, which is 3x minus 2. Okay, so just like f of like 3, for example, this tells us we're going into our function f, and then this x right here is going to get replaced with this entire function. So we're replacing this x with a 3x minus 2. So instead of x squared, we have 3x minus 2 squared, and then plus 3. So this means I need to write it out twice in FOIL. Okay, and then don't forget that little plus 3 on the end. So we're going to FOIL this out. I've got a 3x times 3x, which is 9x squared. 3x times negative 2 is negative 6x. I've got another one of those on the inside. And then last, negative 2 times negative 2. And then, like I said, don't forget my little plus 3 on the end. So for a final answer, we combine up like terms. That would be the first composition. You could also do the opposite composition, which would be g composed with f. That means you're going to take your function g and plug in f, which is x squared plus 3. Okay, so we go into our function g, which is 3x minus 2. And the x gets replaced with x squared plus 3. And then you have a minus 2. So just distribute the 3. And then tack on the minus 2. Then, of course, combine like terms for your final answer here. All right, so from 6.1, that is the operations on functions. We've got 5 operations, and I just covered them all there. Okay, next section we had was 6.2, and this was inverses. All right, so you've got two options for inverses. You've got the easier option, which is when I just give you like a list of ordered pairs. So let's say I give you like 6, -2, and 1, 7, etc. You know, I mean, you could have 3 points, you could have 8 points, it doesn't really matter. If you are asked to find the inverse of that relation, literally all you have to do is swap the x's and y's. The x becomes the y becomes the x. So this ordered pair would become -2, 6. This ordered pair would become 7, 1, etc. You do the exact same thing for all of those. So that's the easiest way that I can ask you to find an inverse. I could also ask you to just find the inverse of a function. So let's say I give you f of x equals 2x minus 6, and I ask you to find the inverse of that function. Okay, so we had a 4-step process that we followed in the notes. First step is instead of f of x, write y. Then we're going to pull a little swap, and this is the important part for the inverse. You replace the y with an x, and you replace the x with a y. Okay, that was step 2. Step 3 is you do whatever algebra you need to do to get this y by itself. So start by adding 6. So we get x plus 6 equals 2y, and then we finish it off by dividing both sides by 2. Okay, so you've got x plus 6 divided by 2. You could also divide each piece by 2. It's like 1/2 x, and then 6 divided by 2 is 3. Okay, last thing is you want to replace it back with that inverse notation, which has a little -1 as a superscript there. Okay, so that would be the inverse of that function. All right, so that sums up the inverse stuff. Inverse stuff, there's not a ton of crazy stuff going on there. The other thing that we did in the section was to find out whether a function was an inverse or whether two functions were inverses of each other. We saw that in the practice test. What you do is you compose f of x with g of x. All right, so if you're looking at any of those, just look at the practice test, the first 4 problems on the practice test. So for example, I can show you. This is the original function, and this is the inverse. If I plugged one into the other, I should just get x. So like, let's take this function, for instance, and plug it into this function. So 1/2, instead of x, I'm going to plug in 2x minus 6, and then finish it off with a plus 3. So simplify this up, start by distributing the 1/2. So 1/2 times 2x is just x. 1/2 times -6 is -3. And then I have a plus 3 on the outside. So hopefully you notice that the 3's cancel each other out and you're just left with an x. And then I can go the other way. If I take this function and replace the x, I'm sorry, other way. If I start with this function and replace the x with this function, I said also just get an x. So 2, replace the x with 1/2 x plus 3, and then minus 6. Here I'm going to distribute the 2. 2 times 1/2 x is just an x. 2 times 3 is 6. And then minus 6. So once again, the constants will cancel out, leaving you just with an x. So if you get x's in both of these composition examples, then they're inverses of each other. And that's how you know. All right, so that's my 6.2 stuff. Let's move on to 6.3. Section 6.3 was all about graphing square root functions and graphing square root inequalities. Okay, so I'll give you guys an example of each. So let's say we wanted to graph f of x equals negative square root of x minus 3. Plus 2. Okay, so we're going to graph that. So we also would have to find the domain and range in these examples. So to find the domain, you take the radicand, which is the stuff underneath the square root, and you set it greater than or equal to 0, because you know we're not allowed to plug anything negative into a square root, so we're guaranteeing that this thing will be positive by setting this up. Then add 3 to both sides, and we know that x has to be greater than or equal to 3, and that's our domain. Okay, and then to find our range, what we're going to do is we're going to plug the 3 in and see what we get as our x value. I'm sorry, our y value. So plug in that 3, and we get negative square root of 3 minus 3, which we know is going to be 0, and then plus 2. So this is all just 0, and then we get 2. So we know that 2 is going to be our beginning y value. So y is going to be something either greater than or equal to 2 or less than or equal to 2. What we do is we look at this right here. Because this is negative, that means my graph is going to be flipped upside down, which means this is going to be a less than or equal to. If my graph is not flipped upside down, it's just a greater than or equal to. All right, so now I'm going to graph. So I start at 3. 1, 2, 3. Remember, x lies, so instead of going to the left 3 units like it seems like we're going to do, we actually go to the right 3 units. And then we go up 2 units. So this right here is my starting point. And then the most important thing to look at for my shape is this negative sign. The negative sign tells me my graph goes down like that instead of up. All right, so you can see that I have only x values that are greater than or equal to 3, and I have only y values that are less than or equal to 2. All right, and that would be the graph. I've got my domain. I've got my range. You'll be asked for those as well. Okay, now the inequalities. Let's graph an inequality. Let's say y has to be greater than the square root of x minus 1 minus 4. Okay, so we're going to graph that. We start it very, very similarly to what we just did here. Okay, so kind of figuring out where we're going to shift. So this x minus 1, remember x lies, so we're going to go 1 unit to the right. And then minus 4, y tells the truth. So we are actually going down 4 units. So that's our starting point. And now let's look at the inequality. I have just a greater than, which means my graph is going to be a dotted line, like that. If you forget, remember, just write me a little note. And then greater than means I shade up above. However, be very, very careful of my domain. Remember, I'm only allowed to use x values that are greater than or equal to 1. So you're actually going to kind of block off the rest of the domain. You're going to block anything on the left here from even considering graphing it. Then we graph up above. And that's our inequality. Oh, I should probably mention we are graphing up above because this is a greater than. Greater than goes above, less than goes below. Okay, so that's 6-3. 6-3 is graphing the square root functions and graphing the square root inequalities. Then we have 6-4. 6-4 was doing some of these nth roots, taking square roots, taking cube roots, taking fourth roots. So a couple of examples here. We had something like this, like the 6th root of x squared plus 3 to the 18th. Okay, so these ones were kind of weird examples. If you're taking the 6th root of something raised to the 18th power, it's like how many times does all this multiply by itself, or what multiplies by itself 6 times to get me this? And what you actually have here, you leave the x squared plus 3 exactly where it is, but what we're trying to figure out is how many copies multiply out 6 times in order to give me 18 copies. The way we figure that out is just by dividing 18 by 3. I'm sorry, 18 by 6. 18 by 6, and we end up with 3. So if you wrote this out 6 times, x squared plus 3 raised to the 3rd, times another copy, 6 times, you would have 3 copies here, 3 copies here 6 times, so you'd end up having 3 times 6 copies, which is where the 18 comes from. So you could see examples like that. We could see examples like this. Okay, so 4th root of a to the 8th. So it's basically the same thing that we're doing up here. If you've got 8 copies, you want to figure out what the 4th root is. How many copies multiply by themselves 4 times to give you 8 copies? Well, 8 divided by 4 gives us 2. So if you did a squared, a squared, a squared, a squared 4 times, that would give you a to the 8th. And then same thing here, you're just dividing indices. So b to the 12th, you divide the 12 by 4, which means that we had 3 copies. Okay, make sure that you know your powers. You really need to know some of these big powers, the squared powers, the third powers, fourth powers. Those are very, very important to know. All right, so I'm going to make you the teeniest little list here that you should definitely know. I'm not even going to write square roots because I'm hoping you know those. So 2 to the 3rd is 8, which means the cube root of 8 is 2. 3 to the 3rd is 27, which means the cube root of 27 is 3. 4 to the 3rd is 64, so the cube root of 64 is 4. 5 to the 3rd is 125, so same thing, cube root of 125 is 5. And we'll stop here with the 6. 6 to the 3rd is 126. Those are the third powers that you should definitely know. Fourth powers, 2 to the 4th is 16. 3 to the 4th is 81. 4 to the 4th is 256. And 5 to the 4th is 625. I think that's probably good with those. So same thing, if you're trying to take the 4th root of one of these numbers, it takes you back to one of these numbers. Like the 4th root of 256 is 4. And some 5th powers. 2 to the 5th is 32. And we could probably stop here with 3 to the 5th. 3 to the 5th is 243. Okay, so just a couple of powers to throw on there. So you should know these if they pop up on the test, okay? Next section, 6.5. 6.5 is all about radical expressions. So adding, subtracting, multiplying, dividing. So some of them you were just simplifying. So let me show you an example like square root of, let's do an 18 a to the 5th, b to the 6th. And let's see. I guess just the square root works for this. So square root of this, and we learned to simplify it up. So this is the one where we wrote out everything. So 18 isn't a perfect square, but 9 is. So we have 9 times 2. 5 copies of A, 6 copies of B. And since we're taking a square root, we're looking for buddies, pairs, things that multiply by themselves. So 3 times 3, A times A times A, B times B, B times B, B times B. So when we're taking the square root of 9 is 3. The square root of A times A is A. Square root of A times A is A. Square root of B times B is B. Square root of B times B is B. Square root of B times B is B. And then the leftovers that don't have buddies are a 2 and an A. Now, you wouldn't leave it like this. A times A is A squared. B times B is B cubed. And then you have a 2A left underneath. Now, notice that this number right here corresponds to the number of pairs right here. And this number right here corresponds to the number of pairs right here. So you could absolutely skip this step. I'm just trying to lay it all out there for you. Okay, let's look at an example of combining like terms. Okay, so combining like terms is combining like radical parts. So right now, none of the radical parts are like at all. But what we can do is all of them have perfect square factors that we can simplify. So square root of 72, for instance. 72 is 36 times 2. 36 is a perfect square. 2, of course, is not. 98 is 49 times 2. 49 is a perfect square. And 50 is 25 times 2, where, of course, 25 is a perfect square. So we've got 6 times the square root of 36, which is 6, and then times the square root of 2, which we can't simplify. And then plus 7 times the square root of 49, which is 7, times the square root of 2, which we can't simplify. And then minus the square root of 25, which is 5, times the square root of 2, which we can't simplify. All right, so a couple more steps. 6 times 6 is 36 root 2, plus 7 times 7 is 49 root 2, and then minus 5 root 2. So if we add these all together, I'd do 36 minus 5 first, and that's 31, and then adding it to 49 is a little easier. So 31 combined with 49 gives me 80. And then don't forget to attach your radical part to it. So 80 times the square root of 2. Now these ones, they all happen to end up with the same radical part. It's definitely possible that you don't end up with the same radical part. And then that just means that you can't combine all of them. But these ones, you could combine all of them. All right, let's do one of these rationalizing ones. About 3 over 5 plus the square root of 2. All right, so these are good ones where you have some sort of radical piece in the denominator. And then what you have to do is multiply by what we call the conjugate. So 5 plus root 2, the conjugate is 5 minus root 2. And of course, whatever you multiply by the denominator, you multiply by the numerator as well. That way, this thing right here, this is just a fancy 1. So when you multiply something by 1, it doesn't change its value. It might look different, it's going to look different, but it's not going to change its value. Okay, so multiply here, distribute the 3. 3 times 5 is 15, minus 3 times root 2 is just 3 root 2. In the denominator, we have a binomial times a binomial, so we're going to have to FOIL. 5 times 5 is 25. Outside is negative 5 root 2. Inside is a positive 5 root 2. And then the last is root 2 times negative root 2, so that gives me a negative 2. Okay, so let's keep cleaning up here. So 15 minus 3 root 2 over, now these will cancel out. Now, one thing people try to do all the time, you can't pick one term from the numerator and one term from the denominator and try to reduce them down. That does not work, I promise you. It's only if everything has a common term that you can reduce it down. So then we just simplify this. 25 and a negative 2 gives me 23, and that would be your answer. Okay, so we've covered a couple of the things here. The basics from this section are being able to simplify square roots like this, being able to add or subtract using common radicals, and being able to multiply and divide. This is kind of like dividing, rationalizing the denominator, and we just practiced a little bit of multiplying in the numerator and denominator. All right, so that's 6-5. 2 sections left to go. 6-6 was all about rational exponents, having fractions as exponents. So let's do a couple of examples from that section. So simplifying each expression, let's look at something like this. X to the 1/2 times x to the 2/3. So say you're trying to simplify something like this. If you've got a base times a base and they've got their own powers, what you do are you add the powers together. So first of all, we can't add 1/2 to 2/3 yet because they have different denominators. So let's start by giving them a common denominator. So the common denominator between 2 and 3 would be 6. So here, multiply 1/2 by 3 over 3, and you get 3 over 6, times x, and then multiply 2 over 3 by 2 over 2, and then you get 4 over 6. All right, so next step, now that they have the same denominator, would be to add them together. So if I add 3 over 6 to 4 over 6, I get 7 over 6. And that would be your final answer. Okay? Some of the other things that we did in this section were kind of simplifying between forms. So let's say that I gave you like an a to the 3/8 or something like that. This is called exponent form, where you literally have your power written as an exponent like this. Radical form, the denominator becomes the index of a radical, and then you keep the numerator with your variable like that. Okay, so we can also do something really, really similar with numbers. Like we might take 16 and raise it to like the 5/2 power, for instance. So what you do is, remember, the denominator becomes the index. That means we're taking a square root, and then you have 16 to the 5th power on the inside. So now you could do 16 to the 5th and then take the square root. However, I would recommend taking the square root of 16 first, then raising it to the 5th power. Just makes it easier. So root 16 is 4. Raise that to the 5th power. So is that even one that I gave you? I didn't. We have 256. So that, I mean, you could just plug something like that into your calculator. But 256 is 4 to the 4th. So times one more copy of 4 would give you this, 1024. Excuse me. Okay, so a couple of things with rational exponents. You basically want to make sure that you're able to do all of the properties of exponents that you learned before, and just kind of convert them into being able to use fractions. All right, so things like this, like if you're multiplying a base times a base, you add their exponents together. If you have something in the numerator and then something separate in the denominator, you would subtract those exponents. So look through this section again. Make sure you know all of the properties of exponents that you're supposed to know. Okay, and our very last section was section 6-7, where we were doing radical equations and radical inequalities. All right, so I definitely want to show you guys one where we have square roots on both sides, because those are ones that are definitely tricky. So I'm going to start you off with this one. Oops, that should be a minus, I'm sorry. Okay, so our first rule that we've been following is isolate the radical. However, there are two radicals, one on each side. So the best thing you can do is isolate one of them. So this one, to get rid of the negative, divide every single bit of these by -1. So negative divided by a negative leaves me with a positive, root x minus 11, equals, and then this becomes a -3, and this becomes a positive root x. All right, so that'll make things just a little bit easier. Next thing is to square both sides, because this is a square root. If it were a cube root, you would cube both sides. If it were a 5th root, for instance, you would raise both sides to the 5th power, whatever the index is. Okay, so here you're going to square both sides. Now, we've talked about the difference between these two. This side, big square root, 2nd power, they cancel each other out. All I have left is an x minus 11. On the right, I have two separate pieces. Only part of it is under a square root. When that's the case, I have to write it out twice in FOIL. You cannot just square both of the pieces. That would not be accurate. Okay, so my left-hand side, just an x minus 11, and then I'm going to FOIL. Negative 3 times negative 3 is 9. Then I have a negative 3 root x. I have another negative 3 root x. And then I have this, root x times root x gives me just an x. Okay, so I'm going to start moving some stuff around. So I have an x here, I have an x here. I could just subtract x from both sides, and they would actually both cancel. Now I have a negative 11 over here. Got a 9. Now I can combine these two up. Negative 3 root x minus 3 root x gives me a negative 6 root x. Okay, now since I have another square root, I need to isolate the radical again. So I want to make sure I'm getting rid of this 9, so I'm going to subtract it. So we've got a negative 20 equals negative 6 root x. Still trying to isolate, so I'm going to divide both sides by a negative 6. So here they have a common 2, so I can reduce this down to positive 10/3 equals root x. And then finally, very last step, to get the x by itself, I'm going to square both sides. So x equals 10 over 3. If I square, I get 100 over 9. 10 squared over 3 squared. So with these, remember with radical equations, you have to check your answer, no matter how confident you are of your algebra. Because I am very confident of my algebra here, but you're still going to check your answer. All right, so we're going to take that 100 divided by 9, and we're going to store it in, which is this control and then the button above the 9. We're going to store it in as x, and then we're going to type in our original equation before we made a single change to it. So negative square root of x minus 11. We want to see if it equals 3 minus the square root of x, okay? Original equation. Now you have to do this with this section because sometimes answers just don't work out. This one did. If you get a false, maybe you did your algebra wrong, but it could also be an extraneous solution. So if you do get a false, do a quick double check. But this one ended up working out. So if you get a true, box it up. That is your answer. If you get a false, I would first double check your algebra. But if you're sure of your algebra, then it means it's extraneous, and I just want you to put a big X through it. Okay? Very last type of problem is these inequality types. Okay, so I'm going to set up one more problem for you. Let's do 2 plus square root of 3x minus 1 has to be less than 5. Okay, so 2 inequalities must be set up. First of all, we take the radicand. If there are multiple radicands, we do this more than once. You take the radicand, and no matter what this sign is, this doesn't matter at all, you set the radicand greater than or equal to 0. Because, just like one of our former sections with the domain and range, we can't plug in anything negative into the square root. So we have to make sure we're not plugging in anything negative. We have to make sure this is positive. So I would add 1 to both sides, and then divide by 3. So this tells me that no matter what I come up with this algebraically, I can't plug in anything that's smaller than 1/3. Because if I do, this would be negative, and then I would be outside of the bounds of real numbers. Say like a 0. Like a 0 is smaller than 1/3. If I tried to plug in a 0, this would be a -1. I can't take the square root of -1 in the real numbers. All right, so I have to restrict myself to this first. Then I go back here and do the algebra. Okay, so subtract 2 from both sides. I get the square root of 3x minus 1. Comes out to be less than 3. The next thing I do is I square both sides. If it were a different power, if I had a 5th root, for instance, I would raise both to the 5th power. This gives me just a 3x minus 1 because this is one big square root. Remember the difference. 3 squared, of course, is 9. Add 1 to both sides. I get 3x has to be less than 10. And then I'm going to divide both sides by 3. And I get x has to be less than 10/3. Okay? So now, this part is very, very, very important. The next thing that you do is you have to look for the overlap between the domain restriction and what you actually got algebraically. Okay, so I'm going to set this up for you. So here's 1/3. Somewhere down the line here is 10/3. So in pink, I'm going to show this restriction right here. So greater than or equal to 1/3 would be closed circle, shaded off to the right. Less than 10/3 would be an open circle, shaded off to the left for less than. Okay? My goal here is to look for the overlap. Here is the overlap, right here, in between those two values. Anytime that I'm in between two values, I set up like this. You literally write x in between two values. Now this, I have a closed circle, so this is an or equal to. Here I have an open circle, so this is not. So this would be your final answer. With the inequalities, you have to make sure that you're looking for the overlap between the two sections. Okay? So that is it. Please do not hesitate to come in and ask me questions if you're still curious about anything. All right?